Greetings, physics enthusiasts. Welcome to AP Physics 2, Unit 6, Lesson 9. We are continuing to talk about light. We've been talking about light bouncing off or reflecting off mirrors and light being transmitted through lenses. And now what we're going to do is we're going to talk about some different characteristics of light, one of which is that light has interference. When I have two light waves. Here's a light wave. And then another light wave. Those light waves can interfere if they both get to the same place at the same time, and they do thusly, then they will interfere constructively. So two little beams of light would be incident on the same location, and it would have a certain brightness with just one, but it would be brighter with two if they were interfering constructively. Crests together, troughs together, crests together, troughs together. But if for one reason one of these light waves got there before the other, they were not in sync, they were out of phase, then this crest and this trough would still interfere, but they would interfere destructively rather than constructively. And this crest and trough would interfere destructively, and this crest and trough would interfere destructively. And as you can see, as one light wave gets a half of a wavelength ahead, or the other one gets a half a wavelength behind, we have destructive interference. But if we were to be a whole wavelength off, then we would have constructive interference again. So when we have interference, if the path difference, and I know this is review, if the path difference, which we call delta, equals one wavelength, or two wavelengths, or three wavelengths, or four wavelengths, or any integer number of wavelengths, where m is an integer, that gives me constructive interference. And if the path difference equals an integer plus 1/2, like 1/2, or 1.5, or 2.5, or 3.5, or 4.5, times a number of wavelengths, that gives me destructive interference. So we're going to look at some examples of that. Now, in order for waves to interfere and have this lovely constructive and destructive interference, one condition is that the waves have to have the same wavelength as one another. These waves do not have the same wavelength, and they're not going to interfere cleanly and clearly like this, because with this crest, we have multiple crests and troughs. That just doesn't work. So we say that we have conditions. We have a loud phone. We have conditions for interference. Two of them. One is that the wavelengths need to be the waves need to be the same wavelength. So they need to have the same wavelength, or there needs to be one wavelength. And so the prefix for one is mono. And since the wavelength of light is associated with the color of that light, we don't call it mono wavelength, we call it monochromatic. So the light needs to be monochromatic, and all the waves, if I have a source of waves, all the waves that are emitted need to be crests together, and then troughs together, and then crests together, and troughs together. My source of light can't just emit everything all randomly. All of the waves emitted by my source need to be emitted crests together and then troughs together. So it has to start out in sync, and the adjective that we use for being emitted in sync is coherent. You might use the word coherent in your literature class when you're writing some essays, and your teacher might say your paragraph needs to be coherent And what that teacher usually means is that all the sentences in the paragraph need to be talking about the same thing. So all together, working as a team, coherent, all of the little waves emitted are working together, all crests together, all troughs together. All right. So that's our introduction, what we need for constructive destructive interference and our conditions for the light. Now, the experiment that we use to prove that light is a wave looks like this. We have a source of light. I'll draw something that looks sort of like a flashlight. A source of light. And then we send that light through a little place here where there are two slits. So this is a wall or a screen that blocks the light everywhere except in these two little places that we call slits. Two slits. A slit is just a small opening. And then we have a screen over here where we observe the light. And there's two ways that you can think about this happening. You could think, okay, so the light travels along and it goes through this slit or it goes through this slit. And if that were to happen, then you might think of the light that goes through this slit coming along over here and making a dot on the screen, and the light that goes through this slit coming along over here and making a dot on the screen. So it certainly would be plausible for you to predict light travels and light either goes through this slit or this slit. If it goes through the top slit, it makes this little dot. If it goes through this slit, it makes this little dot. Now that would be thinking about light as a particle. So if this were what we saw, that would be evidence that light is a particle. And we already have plenty of evidence that light is a particle if you remember the photoelectric effect. But what goes on here in reality is we do not see these two individual dots like this. What happens is that it really seems like all the light goes through here and all the light goes through here. What? And when the light goes through here, it spreads out like a wave and illuminates the screen. And the light that goes through here spreads out like a wave and illuminates the screen. Let's see what that might look like. I'm going to draw it bigger. So if I have my two slits and I have my screen over here, at each location here, I've got light coming from this slit and light coming from this slit. So I could talk about lots of different locations here. I'm just going to talk about one location and see what happens there. But remember, I could do that anywhere. So the light that comes from here goes over and illuminates that location. And the light that comes from here goes over and illuminates that location. Those are supposed to be line segments, not curves. And again, I could do the same thing at all these other locations, but that would be messy. So I'm just looking at this one little point P here. I'm going to draw a dotted line right through the center. And I'm going to call this distance from the center up to my random point P, capital Y. And what we see is that this path is shorter than this path. And what I can do is I can draw this line segment. And we cheat just a little bit here. I'm going to say that this line segment is perpendicular both to this and to this, which of course is impossible because this is a triangle and a triangle cannot have two right angles. But we're really close. We're making an isosceles triangle, so these two paths are the same. And if these two paths are the same length, then this part right here is the very ever important delta, or the path difference. The light came in, it went through both slits and took one of these two paths, the long path and the short path. And the long path is longer by this distance delta. Now we're going to call this distance L from the slits to the screen. And I'm just going to look at my equation over here. Um, pardon me. This angle up here, the angle that we go up, and this angle here are going to be the same. So let me draw this again, just so you can see what angle I'm talking about. Dotted line, screen over here. From the center up to point P, I'm talking about this angle here. And that angle, theta, and this angle, theta, are the same. Do you see if I go straight across, theta is 0? And if I go straight across, this closes down, and this theta is 0. So that means that this distance, which is the hypotenuse of this right triangle, this distance is called little d. It's called the separation between the slits. This delta is d sine theta. That is the path difference. And remember, our path difference needs to be m lambda, an integer number of wavelengths, for constructive interference. So if I'm going to have constructive interference here, this is going to be bright. If this distance here is the wavelength, or twice the wavelength, or 3 times the wavelength, or 4 times the wavelength, that means that this gives me a bright spot. If, on the other hand, if d sine theta equals m plus 1/2 times the wavelength, then I would get a dark spot. And as you can see, as this angle opens up, this path difference gets longer. So I start with a path difference of 0, bright, and then my path difference gets a little bigger, and then a little bigger, and a little bigger, and a little bigger. So I go from bright to dark, to bright, to dark, to bright, to dark. And what I get is stripes. So what I see is brightness, and then where's another color pen? And then darkness, and then brightness, and then darkness, and then brightness, and then darkness. And that goes in both directions. So instead of getting what was a plausible guess, instead of getting 2 bright dots, which would have indicated that light was a particle, I get this alternation, bright, dark, bright, dark, bright, dark, which indicates that light is a wave. It's a wave because it interferes constructively and destructively. That is very hard to see, that word wave, and wave is important. Light is a wave. So that is what's going on there. Now let's see, we said d sine theta equaled m lambda. And then when I drew the picture bigger like this, you can also see that this distance y and this distance L are related to a right triangle as well. Yes. So sine theta. For small angles, this is the sine graph. And this is the tangent graph. And do you see that for small angles right in there, they're pretty close to each other? So for small angles, sine theta equals tangent theta. So we're going to use that small angle approximation here. And I'm going to say tan theta, tangent is opposite over adjacent, y over L. But since sine theta and tan theta are approximately equal to each other, I can say sine theta equals y over L. And that allows me to combine this equation and this equation, each of which have sine theta in them. And I can get another equation, y equals lambda L over D times M. And that just comes from solving this equation for sine theta and this equation for sine theta. So I get y over L for sine theta, and I get M lambda over D for sine theta. So y over L and M lambda over D. All right, and so this is an equation that talks about how far away I have to go from the center to get to the next bright. M equals 0 gives me the center. M equals 1 gives me my first bright stripe. M equals 2 gives me my second bright stripe, and so on. So again, this equation comes from taking these two equations. All right, solve this one for sine theta, solve this one for sine theta, M lambda over D, and set y over L equal to M lambda over D. And here we have y over L equals M lambda over D. Okie dokie. So now, what is this all called? We have to name the person who maybe or maybe not was the first person who did it, but definitely was the first person who got it named after him. Y-O-U-N-G, Young's double slit experiment. Ta-da! So there we have that. I think that is almost everything I need to say. Young's double slit experiment is proof that light is a wave. We already had the photoelectric effect that proved that light is a particle. So light is both a wave and a particle, which we call duality. Light has duality. It is both a wave and a particle. Wave-particle duality. A little bit of vocabulary, and then I shall close for the day, or for this video session. These bright and dark spots or stripes are sometimes called fringes. An odd word, but sometimes they are called fringes. Sometimes the bright places are called maxima, and sometimes the dark places are called minima. So we can use maxima, plural, or minima. Sometimes they're also called stripes, sometimes called fringes, sometimes they're called bands. All of those are synonyms. When you are reading, you need to realize that they all mean the same thing. Sometimes I'll give a whole lesson on fringes, and then the problem in the book will be about bands, and kids are like, what is a band? So anyway, stripes, fringes, bands, all the same. Bright places are called maxima. Bright places are called constructive interference. And there you go. That is all the vocabulary and all the equations that I have for you today. Have a wonderful day. Be careful out there. Don't break any of the laws of physics.